Case E. We talk of oxygen. Special example for oxygen. Oxygen is 0 minus, is equivalent, is a valence, divalent, is a diatomic, and essentially divalent and diatomic gas. So it will now therefore require oxygen is written as 0.2 like this, so 2 times 2, 4. It means 1 mole of oxygen to be liberated will require 4 Faraday. Take note of that. It requires 4 Faradays of electricity to oxygen. So let's see example under oxygen here. Example 1. How many Faraday of electricity is required to liberate 3.2 grams of oxygen gas. Take oxygen is equal to 16. So you all know oxygen gas, it will be 16 times 2. So 16 times 2 grams, that is 1 mole of oxygen, will require how many Faradays? Require 4 Faradays. So meaning 32 grams of oxygen require 4 Faradays. Therefore 3.2 grams of oxygen will be 3.2 times 4 divided by 32. So this one will be 0.4 Faraday of electricity. Let's see example 2. Example 2. Calculate the number or calculate the mass of oxygen gas liberated by passing 9650 coulomb of electricity. Take oxygen is equal to 16. This is another question. So 4 Faraday is required to deposit 32 grams of oxygen. So let me write this as 32 grams of oxygen require 4 Faradays, meaning 4 Faradays, 96500 coulomb. That is what we know. So 4 times 96500 coulomb is required to deposit 32 grams of oxygen gas. D have to liberate. So therefore, we say 9650 coulomb is required to deposit 9650 times 32 divided by 4 times 96500. This will be 0.8. When you divide it, everything will give you 0.8 grams of oxygen. Take note of that. That is example Example. So example 3. Calculate the mass of oxygen that would be liberated by 0.5 farad of electricity. Oxygen, 4 Faraday, 32 gram of oxygen. 16 times 2, that's 32 gram. Therefore, 0.4, this Faraday gives you 0.4 times 32 divided by 4. So it will give you 3.2 gram of oxygen gas. So that is how. Let's see example 4. Let's see this question. A current of 4 ampere was passed through copper 2 sulfate solution for 1 hour. What mass of copper was deposited? Okay, copper is equals to 64. 1 Faraday is equals to 96,500 coulomb. 1,500 coulomb. So we have time is given to be 1 hour. Convert is 3,600 seconds. While I is equals to 4 ampere. So Q is equals to IT. 3600 times 4. Leave it like that. In coulomb. Is a diverless, so it will carry 2 Faraday. So 2 Faraday of electricity will deposit 4 grams of product because it's dying. Two require 2 Faraday. Many 96500 because 1 is given times deposit 64 grams of copper. Therefore, 2,600 times coulomb deposit, let's see, 3600 times 4, then times 64 here, divided by 2 times 96500. So it will give us 4.8. I'll give you 4.8 gram. 4.8 gram. Example 5. 0.222 gram of a divalent metal is deposited when a current of 0.45 ampere is passed through a solution of its salt for 25 minutes. Calculate the relative atomic mass of the metal. Calculate the relative atomic mass of the metal. That is example 5. So we start by saying I is equals to 0.45 ampere. T is equals to 25 minutes. The same thing of 25 times 60 is now in seconds. So this one will be 300 times 5. It will be 1500 seconds. That is time. So our Q is equals to IT. Our high is 0.45 then times 1500. So it will be in coulomb. So they said a divalent metal. It means 2 Faraday is 0.45 times 1500. This one will give us 675 coulomb. So 675 coulomb deposit is 0.222 gram. Therefore, let's look for 2 farad. That's the number of Faraday required to deposit the atomic mass of a divalent element. So we look for 2 Faraday, that is 2 times 96500 coulomb. We required 2 times 96500 times 0.222 divided by 675. When you divide this, it gives you 63.5 grams. So calculate the relative atomic mass. So the relative atomic mass of the metal is 63.5. That is copper. 63.